Bon après-midi. Welcome to this, the 38th annual Anna I. McPherson Scientific Lecture in Physics. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University at the foot of Mount Royal in the heart of beautiful downtown Montreal, where the toilets have remained unrenovated for the past 4 decades, but where digital data flows freely on the airwaves. Before I pass to the department chair to say a few words about the history of this lecture series, I will quickly explain the plan. First, everyone in the Zoom session should take note that your image and/or voice may be recorded or broadcast live via YouTube. If you prefer to be recorded or prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This evening, we will have a 45-minute talk followed by 15 minutes of questions. We'll be taking questions both from within the Zoom session and from the YouTube chat. To ask a question from within the Zoom session, please use the raise hand feature of Zoom. That will put your name to the top of the participants list. I will then call on you to unmute yourself, turn on your video, and ask your question. When you are done with the question, please lower your hand to bring others to the top. During the talk, participants in the Zoom session will remain muted and will not be allowed to unmute. At the end of the talk, you will be freely able to unmute, but please do not do so unless you are called upon. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my associate following the talk. After the Q&A session, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session, will be invited to the après-colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Sangyong, the chair of the Department of Physics, to say a few words about Anna McPherson and the history of the McPherson lectures. Professor Jeon.
Thank you, Bill. Welcome to the 2020 edition of Anna McPherson Lecture in the Department of Physics in McGill. I'm very happy to see you all back from yesterday's fantastic talk. Anna Isabel McPherson obtained her bachelor's degree from McGill in 1921 with first-class honors in mathematics and physics, winning the Anne Morrison Gold Medal. She then went on to obtain her master's degree from McGill under the supervision of Arthur Eve, who was a colleague of Ernest Rutherford. After that, she taught mathematics for a time in a local high school and then went to the University of Chicago to receive her PhD in 1933 under the supervision of A.J. Dempster. In 1940, she joined McGill as a demonstrator, then became sessional lecturer and full-time lecturer in 1943. And then she became an assistant professor in 1947 and associate professor in 1954. After retirement in 1970, she stayed at McGill as an honorary visiting professor until her death in 1979. Altogether, her association with McGill lasted almost 60 years. Her contributions to McGill were not only in teaching, research, and counseling. Upon her death in November 1979, she gave a large sum of money to the university to be used for medical research and for the Department of Physics. The department uses the revenue from this money to support research and also to celebrate the annual Anna McPherson Lecture in Physics in her honor. The mandate of these lectures is to bring distinguished physicists like today's speaker, Professor Mavalvala, to the department for a few days to give 2 lectures as well as to meet with the staff and with the students. In establishing this lectureship, the department is acknowledging Professor McPherson's outstanding generosity and her many valued academic contributions. Her legacy lives on in the many students she educated and the inspiration it provided for many generations of physicists. With that, I'll pass the baton to Professor Jack Childress Sankey, who will introduce the 2020 Anna McPherson lecturer. To you, Jack.
Okay, thank you, Sangyong. It is an especially wonderful pleasure to introduce Professor Nergis Mavalvala as our 2020 McPherson lecturer. And let me begin by thanking her for joining us in a Montreal Zoom session and chatting with us mask-free despite our reputation as Canada's COVID-19 hot zone. I first became aware of her team's work in 2008 when her student gave an invited talk about laser cooling massive objects and how they'd created a column of light that is stiffer than a piece of diamond. That is insane. After the talk, I started asking a series of truly stupid questions, all of which received generous, thoughtful answers. And there was this Nergis person with a huge smile, occasionally interjecting a fun thought or new consideration, but mostly staying out of her students' way. This pattern would continue in later conferences. Fast forward to 2016, LIGO announces their first ever measurement of a gravitational wave. Now let me try to convey the significance of this moment a bit more accurately than I did yesterday, where for whatever dumb reason I wasn't thinking of massive particles as signals from space. What's important is this: gravitational waves represent a fundamentally and qualitatively different kind of signal than everything we've ever observed before. This is certainly a discovery of century scale importance and may well be the most important scientific moment I will see in my lifetime. Anyway, all this to say, Nergis has been a hero of mine since 2008, and as it turns out, I am not alone. After moving from Pakistan to join the US in 1986, she attended Wellesley College, receiving her BSc in 1990, somehow having already published in an APS journal at a time when it was very uncommon to do so. It's still uncommon to do so. She then joined Rainier Weiss's group at MIT, helping lay the foundation for LIGO. And in 1997, she got her PhD, moved to Caltech for a postdoc looking at cosmic microwave backgrounds. And then in 2002, MIT Physics, who clearly missed her, stole her back. And then having the freedom to pursue her own agenda, her career really took off. She is the Curtis and Kathleen Mabel Marble Professor of Astrophysics and Dean of Science at MIT. And notably, she's a MacArthur Fellow, she's a Sloan Fellow, an APS Fellow, and an OSA Fellow. In 2014, she was the LGBTQ Scientist of the Year. And in 2017, she was elected to the National Academy of Sciences. The list goes on, and I was interested to find out that even the Pakistani government, including the Prime Minister, singled her out on a few occasions as a national hero of science. Today, sorry about the toddlers. Today, Professor Mavalvala is giving the McPherson Lecture because of her numerous contributions to gravitational wave astronomy, quantum limited measurement, and insane optical control over the motion of solid objects that you can see with your eyes and hold in your hands, or really heft if you pick up one of the big mirrors. Her team's most recent breakthroughs are particularly impressive, and if you're lucky, she will talk about them today. So without further ado, please join me in welcoming Professor Nergis Mavalvala to the stage.
So thank you very much, Jack, and thank you everyone else for being here today. I'm just going to get my screen share going. So that was a very generous introduction, Jack. Thank you. It's a real honor to be giving the Anna McPherson lecture. My only regret about it is that I am standing here in my basement in Massachusetts, as opposed to on the McGill campus, where I would much rather be. But hopefully in the future we'll get there again, when I think Canada has very wisely closed its border to its southern neighbor. Very good. So let me say a little bit about what I'm going to talk about today. Some of you might have attended my lecture last night, and that was a story about the discovery of gravitational waves and where we were going with astrophysical observations since that time. Today, since that first discovery, today my lecture is really going to be about how we make gravitational wave detectors and how we're making them more and more sensitive. Much of the data that I will show you is the work of literally hundreds of scientists of the LIGO and Virgo collaborations, and much of it in the US in particular has been funded by the National Science Foundation. So my story today actually begins with an iconic graphic that most of you have seen, and I see this particular moment as sort of the birth of gravitational wave astrophysics. This is an image of the signal that the LIGO detectors measured from a binary black hole collision on September 14, 2015. And this really sort of signaled many firsts. It was the first detection of gravitational waves ever. The first time you directly saw the ripples of space-time. It was it was a confirmation of Einstein's theory of general relativity, particularly the dynamical part, the part that wiggles. It was the first observation of binary black hole collisions, and these were observed in real time. And if you look at the scale of the measurement, it was also a real testament to precision measurement, because this was a machine, an interferometric detector that was capable of measuring displacements at the level of an attometer. So this is celebrated as many firsts. Now, I want to really sort of emphasize that this was only just the very beginning. And in fact, this was the moment of birth. And now we're experiencing the lifetime of this completely new way of looking at the universe. So what are we doing there? We're opening a new window to the universe, and my talk today is about how. But before I tell you about how, I do need to tell you about what does it take to open a new window? What does it take to go beyond the first detections? So advanced LIGO is the instrument that made the measurement that I showed you just a moment ago of the first binary black holes. Now, advanced LIGO has been designed to be operated in a series of observing runs that are interspersed with instrument upgrades and improvements. So the first observing run was the one that gave us that first detection, GW 150914. And indeed, in that observing run, which lasted 3 months, there were 2 other binary black hole observations were seen. The next observing run for LIGO was about a year later. And in that observing run, the Virgo detector in Italy, which is a 3-kilometer long detector compared to the LIGO's 4-kilometer long ours, joins the run. And in that observing run, over those roughly 8 months, 9 months, we saw 7 binary black hole collisions, and a now very famous event, which was the first binary neutron star collision, that was GW 170817. And in both of these observing runs, in observing run 1 and 2, roughly the event rate that we were seeing of astrophysical events was about 1 per month. And you can see in the graphic on the right, when you look at observing 1 run and 2, that was roughly the rate. Then comes observing run 3, which after a roughly year and a half long shutdown for improvements, and this was an observing run that should have lasted about a year, and it fell short of a year because of the global pandemic. And in this observing run, we have an event rate, an astrophysical observation of events at a rate of greater than 1 per week. So a very significant increase in the number of events compared to the previous observing runs. And really, the subject of my talk is, how do we do that? What do we do to get there? But before I tell you that, I do want to say a little bit more about the astrophysics that has come out of this. These are just 2 snapshots I'm going to show you of the kinds of signals that LIGO and Virgo have seen. This is the collection of the first 11 that were seen in observing runs 1 and 2, starting with the very first one in the top left corner. And since then, we've seen collisions of binary black holes that have masses that were in different ranges. We've seen objects that have been startlingly far away. We've seen objects with evidence for spin of the black holes. And then at the bottom right was the now iconic binary neutron star observation. And this was a very special event because it was the only time that we've actually seen light emitted by the same source that we measured gravitational waves from, and that has given us an incredible wealth of information about neutron star physics, and indeed about the origins of chemistry on our own Earth. But that's not the topic of my talk today. Hopefully you heard a little bit about that yesterday. I also want to point out this graphic, which is on the left. You see what's been going on in what went on in observing run 3, and you see a range of different kinds of objects. And I would like to just point out to you, I've highlighted 2 objects that I think are very special and interesting that have appeared in recent publications from the LIGO and Virgo collaborations. On the top right is GW 1905-21, and it's very special because it's our first evidence of something that's called an intermediate mass black hole. So the processes by which these stellar mass black holes form is usually from the collapse of stars. And stars, ordinary stars, even rather large ones, usually do not grow to be larger than a few tens of solar masses, if that. And so to see a pair of black holes, with 85 and 66 times the mass of our sun, actually, orbiting each other and colliding has been a surprise. And certainly the new object that was formed, this 142 solar mass black hole, is something that there were certainly reasons to expect that it should not be possible to do, in particular from stellar collapse, because it turns out that stars of that mass do not, they go through something called a pair instability, and they don't usually collapse. So this is the first time we've seen evidence for an intermediate mass black hole, and we've also seen a little bit about how nature might make one, which would be through the merger of lighter black holes. On the bottom right is GW 1908-14, and that's also a very special object because there is a mass gap somewhere between 2 and 5 solar masses. There is an expectation that greater than 2 solar masses is too heavy for a collapsed object to be a neutron star. And until now, we haven't had much evidence for black holes that are lighter than about 5 solar masses. And this has been called the lower mass gap. And so this is the first event where we have seen a 2.6 solar mass object. And, it's an object. Is it a neutron star? Is it a black hole? And so this is the kind of things that these instruments are starting to tell us about the universe. And the more we want to know about the universe, there's one thing that we must continuously do, and that is to make better instruments with more sensitivity, with more bandwidth, and with greater runtime. So how do we go about making the gravitational wave measurement? So our job is to measure displacements or changes in space-time distances of 10 to the minus 18 meters. That is the scale set by the amplitude of gravitational waves from garden variety neutron stars and black holes in galaxies not too far from our own. So with that as the benchmark, there are 2 things that we must do to build a gravitational wave detector. The very first is, so the principle of the measurement in a gravitational wave detector is simply that we shine laser light at a mirror. The mirror reflects the light back, and if we have a very good clock, we can just measure the light travel time. When the gravitational wave comes by, that light travel time will change, and our very accurate clock will measure that time change. It turns out clocks are not precise enough to do that. So in fact, what we do is an interferometric measurement where we send light down 2 arms of an interferometer, and we simply use one arm as a reference to measure the light travel time of the other arm. So the 2 ingredients that we need then is we do need mirrors that are very, very still enough that they're only moving under the influence of the passing gravitational wave and not due to terrestrial effects. And that brings us to our first factor of a trillion. The first factor of the trillion is in the mechanical motion of the mirror. Now, if you take a typical mirror in a laboratory setting, it will move by several tens of nanometers to about a micron, depending on what frequency of motion you're interested in. Now, to make a measurement of 10 to the minus 18 meters, that means we had to isolate the mirrors of LIGO by a factor of a trillion. And we do that in a couple of different ways. We isolate them on we first place the mirror holder on a vibration isolation platform, and then we actually hang the mirrors in a cascade of pendulums with a resonance frequency of about 1 Hertz. And when we do that, we can achieve this mirrors that are still, or whose motion is smaller than about 10 to the minus 18 meters, right around 100 Hertz. That's LIGO's sweet spot. That's where it has the minimum of motion of displacement of the mirrors due to terrestrial effects. Now, having done that, we still have to measure this tiny effect, this 10 to the minus 18 meters of displacement. And we do that using laser light. Again, the laser light that we use has a wavelength of about 1 micron, and that gives us our second factor of a trillion. We have to be able to resolve the optical fringe, or resolve differences in the amplitude of light at the level of a part in 10 to the 12. And we do that by using very high laser power, so we can average over the fluctuations of our Poisson distributed laser light, where the noise in the laser light goes as the square root of the power. And indeed, in LIGO, we do a trick where we actually, within the 4-kilometer long arms of LIGO, we have 2 mirrors facing each other, and we let the light bounce multiple times between those 2 mirrors to build up the instantaneous power. And so when all is said and done, LIGO will have nearly a megawatt, 750 kilowatts of laser power circulating. Now, when you do all of that, you can come up with a set of curves like this. So LIGO was always built to be, was always designed to be built in phases. The first phase of LIGO is the green curve. That was called initial LIGO, and it ran from 2000 to 2010. Before I go on with the curves, I should just introduce, on the horizontal axis is frequency. And in this case, it's the frequency of the gravitational wave you would like to measure. On the vertical axis is the strain, which is the amplitude of the gravitational wave, or change in length per length. And it's given in units of spectral density, so in units of per bandwidth. So the green curve was initial LIGO. This was a phase that was completed in 2010 and gave no positive detections. Then LIGO shut down for 5 years to come to install a very significant upgrade called Advanced LIGO. And the sensitivity of Advanced LIGO is shown in the 2 reddish curves. And that was the sensitivity that was present when we made the first discovery. Now, the target design sensitivity for Advanced LIGO is the blue curve. And then there are already ideas for upgrades that I'll say more about. That's the cyan curve. So the whole name of the game, if you look at these curves, is we're always going down, which means getting better in sensitivity, and we're also always trying to make the curves wider so we get a more broadband instrument to observe gravitational waves of many frequencies, because different sources have gravitational wave emission at different frequencies. So how do we do this? To understand how improvements happen in the instrument, I have to tell you a little bit about noise sources in Advanced LIGO. This is kind of a slightly busy plot, but I want to draw your attention to just a couple of curves. So the very topmost curve is the black curve, and that is the target design sensitivity of Advanced LIGO that I showed as a blue curve in the previous slide. Now, what makes that up, that black curve? Primarily 2 things. Most of that black curve is made up of the purple curve that's right under it, the magenta-ish purple curve that's right under it, called quantum noise. So for most of the frequencies of Advanced LIGO, it is limited by this noise source that we call quantum noise, and I'll say what it is in a short bit. In a small amount of intermediate frequency band, right around 60-ish Hertz, you also see the red curve contributing, and that red curve is actually the Brownian motion of the coatings, the optical coatings of the LIGO mirror. That is, so thermally driven motion of the surfaces of the mirror, and that gives us some contribution right around 60-ish Hertz. Now, there's one other noise source that I think is interesting to point out in here, and that's the green curve. The green curve is labeled on this plot as gravity gradient. So it's this curve right here. It goes down like this at low frequencies, the solid green curve. It's also sometimes known as Newtonian noise, and this is actually a very important noise source for understanding why one needs to have gravitational wave detectors in space. This is a noise source that's really fundamental. It's actually due to fluctuations in local G. And these could be due to clouds going overhead above your detector and just changing the local gravitational field distribution. It could be seismic waves running, deep underneath your detector. This is the reason that you can't make a really low frequency detector here on the Earth. And later, when I talk about the space detector, this is why. Okay, if you want to go to something lower than about 5 hertz, maybe 1 hertz, you just have to get off the planet. Right? Okay, now quantum noise. The rest of what I'm going to focus on is quantum noise, because as you can see, it's pretty darn important. It's the thing that is limiting advanced LIGO at its design sensitivity. So what makes up this quantum noise? Well, there are 2 pieces to it. On the one hand, where I told you we'd like to use lots and lots of laser power to minimize the shot noise. And the shot noise is simply the Poisson distributed noise of the laser, the square root of the number of photons that are participating in your measurement. And at high frequencies, so typically above about 100-ish hertz, this is the shot noise right here. And if you want to make that noise source get smaller, you increase your laser power. And what that does is it means you're making a stronger measurements. You are more strongly probing the position of the mirror with light. Now, the Heisenberg uncertainty principle tells you that you must pay a price for that. There must be a quantum back action. And what that back action is that as you increase the number of photons that are hitting your mirror, because you're trying to make a stronger measurement, the radiation pressure force from the momentum transfer from those photons kicks your mirror. And that's the back action. That's the Heisenberg uncertainty principle at play here. So at the lower frequency end of this curve, you're limited by this radiation pressure noise. On the one hand, you use more laser power to make a stronger measurement. On the other hand, that stronger measurement means you have to have a larger back action. And this is the trade-off that we continuously have to deal with when we look at quantum noise. I will say that there is a concept called the standard quantum limit. And in this instance, the standard quantum limit, which I'll tell you, it's just a benchmark. It's kind of rather poorly named. It appears in the literature. It's rather poorly named because it's neither standard. Every field has their own standard quantum limit, and it's not really a limit either. It's a sort of it's the balance between radiation pressure noise and shot noise. So for any given power, that there is a minimum measurement that you can have given by the Heisenberg uncertainty principle. So that's where the noise in advanced LIGO comes from. Let's understand in this way. Let's understand its real origin. To understand its origin, we need to do a couple of things. We need to understand how the noise originates. And I'm going to now tell you something that when the first time you hear this kind of blows your mind. So this is a moment to sort of sit up. And so most of you have heard that empty space isn't empty, but it is filled with quantum vacuum fluctuations. This is the process by which particles are constantly being created and annihilated as is energetically favorable with the quantum vacuum. Now, these quantum vacuum fluctuations aren't just an artist's conception. They aren't just a physicist's fiction. They actually manifest themselves in measurements. And famously, they are responsible for the spontaneous emission in atoms. But they also show up, believe it or not, in precision measurements like gravitational wave detectors. So here is how they show up. If you take a laser interferometer, and here I've shown a laser interferometer where you have the red is the laser light and it's split on a beam splitter, it reflects off of the two mirrors. And then by the symmetry of the beam splitter, this laser light is arranged to always go back to the laser. And that means all of the noise on the laser, all the classical noise also went back towards the laser if you had this ideal interferometer. In the quantum description of an interferometer, however, you have an open port where your laser is not. And this open port is always flooded with these quantum vacuum fluctuations. The vacuum fluctuations are depicted as green lines here, and they enter this interferometer, and by the same symmetries of the beam splitter that sent all the laser backlight to the laser, all the vacuum fluctuations come back out at the port they entered. Now, if a gravitational wave comes by and displaces these mirrors so that a little bit of the laser light comes out at this output port, that light will, this coherent field will interfere with the vacuum field, and that's what gives rise to the quantum fluctuations. Now, you can also create certain exotic states of light called squeeze states of light that can alter the properties by manipulating the noise distribution that's given by the Heisenberg uncertainty principle. And if you look at light as a wave, then this picture kind of shows what you might expect. So if you had a completely classical light wave, it would just be this solid black line. It has no uncertainty on it. If you then depict that as a quantum field, then it has some minimum uncertainty associated with it, and your solid black line becomes the gray dashed band, and you can see that it has uncertainty at every part of the wave. But then you can engineer very special states of light where you can make the uncertainty at the peaks become very, very small. So you squeeze the noise in amplitude, but you make the noise at the zero crossings very, very large. And that's what you see in this case here. You can also do the converse. You make the amplitude noise very large, but you make the zero crossings very precise. You make the phase very precise. And those are called squeeze states of light. Now, if you take the same picture and you turn this into a phase space depiction, this is what it would look like. Here is a phase space diagram. X1 and X2 are simply just, you can think of them as the real and imaginary part of your quantum field. And you can see that this has the vacuum state has some minimum uncertainty, equal uncertainty in both along both quadratures. It enters the interferometer, it exits, and the yellow phasor here depicts a signal field. The vacuum field superposes on the signal field, and you have noise in the measurement. And that noise is manifest as you're not being able to measure the tip of the yellow phasor very well. It's blurred out by the quantum noise. Now, you could instead, and this, by the way, gives rise to the shot noise at the measurement output at the output state. This also, by the way, gives rise to the radiation pressure noise. The exact same process is happening at each mirror as well, where this bright coherent field superposes with the vacuum field and causes those vacuum fluctuations are then imprinted on the motion of the mirror as well. Now, you could get around this by using those squeeze states, and in phase space, the squeeze state looks like this. Instead of a circle, it's an ellipse. And if you carefully engineer the ellipse so that the narrowest part of the ellipse is projected onto your signal phasor, then you can make a measurement that's better, has lower signal to noise than if you simply use the ordinary vacuum state. Now, make no mistake, there's no free lunch here. If instead of my signal being along the X2 quadrature, as is shown here, if it were along the X1 quadrature, I would measure increased noise. So anytime I have any fluctuations in the direction in which my signal phasor points, that would lead to this improvement being destroyed. This idea was given to us by Carl Caves in 1980, and it was one of the things that was is still not to this day not appreciated, but was already in his 1981 paper I highlight here. The key requirement of the squeeze state technique is that the state of light entering the interferometer's normally unused input port must not be vacuum, but a squeeze state. So key idea here, we're not squeezing the laser light, we're actually having to squeeze the quantum vacuum state. Now, fast forward from 1981 to about 2015, 2016, and in fact, actually, this data is from more like 2019. So this is now implementation of squeezing in advanced LIGO. On the left, I have a picture of what a squeeze light source looks like. For our purposes, it's all you need to pay attention to is you have this big green box here. That's the interferometer. And then on the bottom right, you have a squeeze light source. And this squeeze light source is injected into the output port of the interferometer. The laser is the red thing coming in from the bottom, and the squeeze light source is coming in from the light. That's also the port at which the gravitational wave measurement is made on the very upper right corner. So I won't say much about how the squeeze light source is made, the squeeze vacuum source is made, but when you do that, then I draw your attention to the plot on the right, where the black curve is what you have is the sensitivity, is the noise in advanced LIGO when you have no squeezing. And then the green curve is the noise you have when you inject this squeeze light source. And you can see certainly at most frequencies above about 60 hertz, you see an improvement in the sensitivity, and those are the frequencies at which you have quantum noise that is being improved by the squeeze light source. Now, if you take the black curve, that's the advanced LIGO curve without squeezing, and you model what the quantum noise should be for those set of parameters, you get the magenta dashed curve. And you can see that it is not quantum noise limited at all frequencies, and certainly above about 100 hertz, the quantum noise is not the dominant noise source. And in fact, if you subtract out the purple dashed model curve from the black curve, you get the gray curve, and that tells you what are the non-quantum noises present in that data. Okay, so the classical noises. And so this is now, let me say, when I showed you that curve earlier of how the event rate went up dramatically in observing run 3, this is one of the key technologies that enabled that improvement, was the injection of squeeze states of light. And that was a major contributor to being able to detect roughly 5 events per month instead of about 1 event per month in the previous observing runs. And this is published in a PRL by my students Maggie Say and How to New and many others. Now, if I draw, and there they are installing their squeezer, there's Maggie in the foreground. Now, if I draw your attention to the graphic on the right, I want to use, so this is the same thing I've shown previously with small variations. The blue is when we have no squeezing, and the red or orange, depending on your screen, is when we have squeezing. And now I want to draw your attention to the low frequency end. And you see something rather troubling. You see that when we inject squeezing, we indeed make an improvement at high frequencies, but at lower frequencies, the red curve goes above the blue curve. The squeeze state is actually increasing our noise rather than decreasing it. And this is, friends, again, a moment to sit up. This is the quantum back action. This is that radiation pressure noise starting to push on the mirrors. This is Heisenberg uncertainty in action, because at low frequencies, what we did was we are sampling the narrowest part of the ellipse, But as we go to at high frequencies, we're sampling the narrowest part of the ellipse. We have injected a squeeze state that optimizes for phase, and then at the anti-squeezing part, the longer part projection of our ellipse is causing the low frequency noise to be higher. So this is quantum back action staring us in the face. So now comes, and this, by the way, was also told to us by Carl Caves in 1980, who told us in this paper that there has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. And this is a measurement of gravitational waves. This letter resolves the controversy. They do. Now, I can never tire of saying how much I love this abstract. Every one of us would love to be able to write an abstract like that. Resolves the controversy. They do. But the evidence for this, has come many decades later, and that was one manifestation of it that I showed you in the previous curve. So I want to now kind of ask a question, which is radiation pressure really a scourge? Is this just this horrible thing that destroys and ruins our measurement and there's nothing more we can do? Or can it also be a force for good? So let's take a look. And I'm going to argue that, in fact, radiation pressure can also be a force for good. I've just shown you its detrimental effect. It is starting to hurt our sensitivity at low frequencies, but maybe there's something more we can do. So to think about radiation pressure and it's the good side of it, I'll introduce another concept, and this is called ponderomotive squeezing, or sometimes also known as optomechanical squeezing. So ponderomotive force, the ponderomotive force is an old-fashioned word for radiation pressure force. It took me a long time to figure that out, but it shows up in the literature as such. So what is ponderomotive squeezing? So the first thing you should know about a squeeze state is that to make a squeeze state, you have to usually correlate amplitude and phase fluctuations, so that you can't just make the whole circle in phase space larger and smaller. That's just classical amplification. To make a squeeze state, what you really are doing is you have to make the amplitude smaller whilst making the phase noise larger, or vice versa, and that means you have to correlate the two. So here's one way in which you could make this correlation. You start off with a laser beam, and you have a movable mirror. This paddle-looking thing is a movable mirror. It's part of an optical cavity, so the large stationary mirror is just there to form the cavity. Now, when you inject light, when that light is incident on this movable mirror, you start off with light that has ordinary, vacuum fluctuations. So you see the circle in phase space, and the large arrow simply says you have a strong, coherent light field. It's got a real amplitude and phase associated with it, and that light field has fluctuations in the number of photons, or it's delta n. Okay, so that's the fluctuations in the number of photons. Those fluctuating number of photons apply a fluctuating force on the movable mirror. The fluctuating force, in turn, makes the mirror move, so it displaces it. When the mirror displaces it and it reflects the light, it changes the phase of the light. So now you get a fluctuation in the phase of the light. And that is the thing that creates the correlation. You are correlating fluctuations in the amplitude of the light to fluctuations in the phase of the light. And that will give rise to a squeezed state. That's how you make a squeeze state optomechanically. And so you can think of this as this process of amplitude applying a force, applying a displacement, in turn creating a phase shift. As you can think of it as creating a phase space shear for this vacuum state. So the normal state that's usually a circle in phase space becomes sheared. It can be sheared into an ellipse and rotated as well. And then depending on how that circle or ellipse projects onto your measurement, as you can see by the arrows on the right of this graphic, you can get more or less noise depending on that projection. And that's the principle of ponderomotive squeezing. So the first result I'm going to show you is this is not just a crazy idea. This actually works. And so this is an experiment where that was done in collaboration with Thomas Corbett's group at Louisiana State University, where we actually take, this is a busy plot. Look at the purple box. That's a little cavity, just like the one I've shown you before. One of the mirrors of the cavity is a very light and a microscopic mirror, and that makes it easy to move under the influence of radiation pressure, this microscopic mirror. And then with applying the right kind of readout and using the radiation pressure force on that little microscopic mirror, we can measure, these are the details of the experiment, but the plot on the right shows you can measure squeezing. So this is a plot that shows frequency on the horizontal axis, and on the vertical axis, we show the total noise relative to shot noise. And shot noise in this case is the ordinary unsqueezed vacuum. That's this solid line on the or the blue curve and horizontal one. And anything you see that goes below that line shows that we have squeezing. And everything that goes above it, of course, is we have anti-squeezing. So the long part of the ellipse is above the horizontal line, and the narrowest part of the ellipse is below. And so you can see that you really can make a squeeze state using this radiation pressure force. Now you can take this one step further, and you can ask, well, LIGO has a ridiculous amount of radiation pressure, because in LIGO, even though the mirrors of LIGO are 40 kilograms in mass, 35 centimeters big, and you would say, okay, what can possibly push those around? There's enough light, with the hundreds of kilowatts of light that is circulating, the laser power that's circulating and hitting those mirrors, the radiation pressure is a big effect. And so the next thing I'm going to show you is something where we use this radiation pressure effect to actually show that you can improve the sensitivity of a gravitational wave detector by using correlations caused by the radiation pressure. So how do we do that? So we look at these quantum correlations, and we are going to address this concept I had introduced earlier, which was the standard quantum limit. So let me just say what that is again. So measurement and back action. Repeated measurements of position are imprecise. That's what Heisenberg tells us, right? And when you make a position measurement, that's the shot noise. The momentum kicks is the back action, and that's the radiation pressure noise. And so we refer to those as shot noise and QRPN, which is this quantum radiation pressure noise. It's the quantum fluctuations of the light that are causing the mirror to be kicked around. Okay, so that concept I've already set up for you. Now, if the shot noise and the quantum radiation pressure noise are uncorrelated, then their balance gives the standard quantum limit. And it's quite an interesting, fundamentally interesting question, right? Because the standard quantum limit is asking the following question. It's saying, if you use light to measure the position of a particle, what's the best you can do? And now you know why there is a limit, because you're tempted to increase the laser power to make a more stronger measurement. But then, of course, you have to grapple with the back action of that measurement. Now, when the shot noise and quantum radiation pressure noise are correlated, then that limit can be surpassed. Okay, and that's the key to the next set of measurements that I'm going to show you, which is how do you create correlations between these two quadratures of light. And the way we do that is this ponderomotive squeezing effect. So I just showed you an experiment where we used a microscopic mirror and showed you that ponderomotive squeezing is real. We can measure it. Now, ponderomotive squeezing is also happening in the LIGO interferometer because of the movable mirror and the large amount of laser power. And we can use that to our advantage to make a measurement that's more precise than the standard quantum limit. So I want you to sort of sort out two things that are going to happen in the next measurement. On the one hand, we're going to inject the squeeze state of light that I showed you earlier. We're going to go into the output port and inject squeeze state of light. At the same time, the laser light that's propagating in the interferometer is also being squeezed by the ponderomotive squeezing effect. So there are two squeezing effects going on, and those two together, because of the, will combine together to give us an improvement in sensitivity. And that improvement in sensitivity comes because of the ponderomotive squeezing, which is due to the correlations created by the motion of these 40-kilogram mirrors. So here's the measurement. On the left, I show a laser, and you can see that's the advanced LIGO interferometer with a bunch of mirrors, etc., that I won't go into. We have a squeeze light source that's going into the output port, and then at the readout, we make a measurement. And now, what do we measure? And that's the graphic on the right. So what you see are a few interesting curves. The black curve is the total noise of the interferometer when you have no squeezing injected, and I've shown you that before. The blue solid curve is the quantum noise model. Again, I've shown you that before. And when you then arrange this, the squeeze state that you're injected to be rotated so that the squeezing ellipse is oriented optimally, and in our case, it turned out to be 35 degrees, which is shown here, you can, in fact, create this dark, on my screen, it's purple curve, that's the model, but it's the green curve, that's the data. The green curve shows you that at 40 hertz, you can actually make a measurement that's much more precise than you would be allowed by just the standard quantum limit, which is the red dashed curve. What we have done in showing you this measurement is about 3 dB or square root of 2 below the standard quantum limit at 40 hertz. What we have done is we have taken the squeeze state that we inject, and we have used the quantum correlations created by the motion of the 40-kilogram mirrors to project that squeeze state in a way that lets us make an even more precise measurement right at 40 hertz. Now, this is just a demonstration to show that the technique works. This is not something you would really want to do very often in a gravitational wave detector, because look at higher frequencies. Notice that the green curve is well above the gray curve, and in fact, you actually lose sensitivity. But it is a method by which you can improve the sensitivity at certain frequencies. And even more exciting to me when I wear my quantum physicist hat is it's a demonstration of quantum correlations on the human scale. These 40-kilogram mirrors of LIGO are being moved by the quantum vacuum, and that is creating the correlations we need to make this measurement. All right. I won't go into the details of how the measurement is made. Now I want to answer one last question, which is how do we make a broadband improvement to advanced LIGO? I just showed you that in a narrow band around 40 hertz, we can use quantum correlations. I also told you it's exciting in an even more fundamental way. But if you really wanted to make broadband improvement, here's what you have to do. So the blue curve that I show you here is advanced LIGO without any squeezing involved. And then the red curve is what we get when we inject the squeeze state of the kind that I have been showing you all along. Now, as promised, you see at high frequencies, you make an improvement, but at low frequencies, your red curve goes above your blue curve, and in fact, your squeeze state is making it worse. And the reason is something I've said before, but I'll show you pictorially so you sort of carry it away in your gut, which is at high frequencies, your signal lines up with the narrow part of the ellipse when the ellipse is in this phase squeeze condition. At low frequencies, if you wanted to not ruin the sensitivity, you need a squeeze state that's amplitude squeeze, because remember, it's the amplitude fluctuations that drive the mirror. And at intermediate frequencies, you need a squeezing ellipse that's rotated at some intermediate angle. And if you could do that, if you could make this frequency-dependent rotation of the squeezing that you inject, then you could get broadband improvement. You could get improvement over all frequencies, which is given by this black curve. Now, the squeeze light sources that we have actually don't know how to do that. You make a squeeze state, and it's it's the same orientation of the squeezing ellipse for all frequencies. So we went about trying to determine how to make this frequency dependent rotation, and it turns out that there is a tool that lets you do that, and that is an optical cavity. So this is a very busy plot, but I'm just going to show you one quick thing, and that's this green box on the left here, where you start off with a squeeze state. And when you reflect that squeeze state of an optical cavity has the property that it has a frequency dependent reflectivity. So if you look at the reflectivity of the cavity on the graphic on the right, the amplitude is given by this Lorentzian, and there's also a phase shift associated with it. So as the light reflects off of this cavity, it gets a frequency dependent phase shift, and that's what you need to make this frequency dependent rotation. And when we did that experiment, you can see as a proof of principle here that we were able to, you can see from the ellipses shown at the bottom at each frequency, that shows you that at each frequency, that is the orientation of the squeezing ellipse. And that set of colored curves corresponds to the projection of each of those ellipses. And the things that is most important is the locus of those curves, which is the solid black curve. That shows you, again, 0 dB in this plot is no squeezing or ordinary vacuum. Anytime you go below ordinary vacuum, you have a squeeze state. And this shows us that we have a squeeze state at all frequencies. Now, you can say, well, your squeeze state got a little bit worse when you get to just a little above a kilohertz. You have a good amount of squeezing at high frequencies and much less. And that is to be expected, because that is the frequency at which the light that's the line width of the cavity. So that's the frequency at which the light starts to couple to the cavity, and the cavity losses destroy some of your squeezing. So that was a proof of principle for how you can make frequency dependent squeezing. And the idea now is to take this kind of cavity, it's called a filter cavity. You take your squeeze light source, pass it through the filter cavity, and then inject it into the interferometer. And that's the plan. So if you look at this curve that I've shown before, I showed you initial LIGO was green, the red curve is advanced LIGO, the blue curve is the advanced LIGO design sensitivity. And then when you ask what was the cyan curve is what we call the A+, or the advanced plus upgrade, which includes frequency dependent squeezing. So the squeezing alone would give you improvement at high frequencies, but this frequency dependent squeezing, where we pass it through this rotation cavity, will give us the low frequency improvement as well. And that's sort of where we're heading with advanced LIGO and these quantum technologies right now. So advanced LIGO is about to go into observing run 4, and A+, I say about to, this is 2 years away. A+ is a significant upgrade to advanced LIGO. And so observing run 4 should begin in 2022 with COVID. There's a lot of uncertainty about that. But the main improvements there will be that we'll use higher laser power and use this frequency dependent squeezing technique. And you can see the curves on the right tell you roughly where we're headed. The blue curve was observing run 2, the orangish curves are observing run 3. The green curve is the advanced LIGO target sensitivity, and then the red curve is this A+ upgrade that's expected to be commissioned by the end of 2023. And there, the plan is to use frequency-dependent squeezing and to also use new optical coatings on the mirrors to reduce the coating thermal noise as well. So that's where we're heading in the near-ish future. There's a global network of instruments coming up. The LIGO instruments you can see on the bottom is the year, and we are roughly right here in the middle to third quarter of 2020. And advanced LIGO and Virgo have completed observing run 3. These numbers, by the way, the MPCs stand for megaparsecs, and that's just a benchmark for the distance to which each of these instruments could see a binary neutron star collision. So the distance is just a way of benchmarking our sensitivity. And you can see as this decade continues that in roughly 2025, advanced LIGO will reach its A+ sensitivity. Virgo is planning also to make some upgrades. The Japanese detector Kagra should be on the air with sensitivity comparable to what LIGO has now, and LIGO India will also be coming on the air sort of towards the latter half of this decade. Then beyond advanced LIGO and Virgo, there is a concepts for a new generation of detectors, which are called third generation detectors. And these are the one knob that's being turned for these is they're going to be made longer, so 10 to 40 kilometers long. And they will have these quantum enhancement technologies that I've shown you, correlations, squeezing, and also some novel mirror designs that are under development. So the interesting thing on this slide is the plot on the bottom left, where the very topmost plot is advanced LIGO during observing run 3, and then you can see advanced LIGO at its design. Then the A+ is the blue, and then when you get to these longer instruments, those are Cosmic Explorer and Einstein telescope, and you can see the sensitivity in those cases improves by roughly a factor of 10 or more, or even quite a bit more at lower frequencies. Now, the thing that's really exciting about these curves and is that the technologies for them are quite plausible. And when you build such an instrument, so imagine you take Cosmic Explorer, which is the red curve. One of the science targets that it can deliver is that it can map out binary black hole mergers all the way to a redshift of 10. And this is really exciting because the redshift of 10 is about the distance or the age of the universe when the first stars formed. So if you can map out all of these stellar mass binary black holes out to a redshift of 10, it's likely you're mapping out all binary stellar mass black holes that exist. And I find that somehow really mind-boggling that, if these instruments are built in the next, say, 20 years, that means in our lifetimes of seeing the very first gravitational wave from binary black holes, we might even see the most distant one we ever could see. And that really really blows my mind that a field could grow that quickly in terms of being able to map out objects in the universe. There are many other science targets for these instruments, but this is the one that I chose to highlight here today. So I'm going to finish my talk just by telling you really quickly about space detectors. There is a plan for the Laser Interferometer Space Antenna, which is a constellation of 3 spacecraft that fly 1 to 5 million kilometers apart. And the concept for LISA is, remember, I told you if you wanted to have a low frequency detector, you have to get off the Earth below about a hertz. The technologies that we currently know are not good enough to get around that Newtonian noise background. And the graphic on the right kind of shows you what the targets are for LISA that are different, the astrophysical targets, which are different than the terrestrial detectors, in particular supermassive binary black holes rather than stellar mass black holes. That's one of the target objects for LISA to look at. Very quickly, without going into details, LISA has a 2034, planned launch date. It had a very successful test mission, a space flight that was supposed to test some critical LISA technologies. And the only thing I will point out to you is the graphic on the left. That's really, even if I don't tell you what it is, it's actually acceleration noise of the LISA test masses. But the thing I want to draw your attention to is that the requirement for the pathfinder was the little triangle at the top. The requirement for LISA itself is the larger shaded region, and the performance of the Pathfinder exceeded the LISA requirement and certainly the Pathfinder requirement. So that technology is on good footing, and LISA is, we hope it will fly again, I hope in my lifetime. So I'm going to finish just by telling you that there's a brilliantly dark and warped future ahead of us. You've seen observing Advanced LIGO observing Run 3, the quantum technologies are working, and this is what we need to get to the next level of sensitivity. The A+ upgrade is actually, we're ready to implement it starting right about now. And then planning and design of these future direct detectors is going on across the globe as well. And then, of course, we also are very excited about the space detector LISA. So I'll stop there, and I'm happy to take questions.
Okay, thank you very much, Professor Mavalvala, for this excellent talk. I really would encourage everyone in the Zoom session to just write something in the chat box to say how much you appreciated both this talk and the talk last night, if you did appreciate them. So please ensure that your anti-squeezed quadrature is injecting noise into the Zoom chat box. Those on YouTube, if you enjoyed the talk, please say so in the chat also. It would be great for Professor Mavalvala to see these later. I will share the chat in Zoom with her so that she can see all of the appreciation that you're showing. If it's okay with you, I guess we can start on the question session. I'll just remind people in the Zoom session that if you're interested in asking a question in person, all you have to do is raise the hand icon. That'll bring your name to the top, and I'll pick you off one by one. Those on YouTube who would like to ask questions, please just type them into the chat and my assistant will relay them to me. I've already got a few lined up. So we're ready to go if you're ready. So here's the first question. First question, I'm going to read out, I think, what the intended question is, and then there are some brackets that I'll explain. The intended question, I think, is how much time do you spend doing research? And then it turns out that the question is written, how much time, if any, do you spend doing research? So I think you can answer that probably well.
Yeah, so the only way to answer that question would be if you asked, there has to be a temporal part to that question. Obviously, in the early part of my career, I spent all my time in the lab. Now, in this phase of my career, my students spend all their time in the lab, and I myself actually don't get to the lab as often as I would like, but I kind of run the group, and occasionally I show up in the lab. I'll tell you what the real difference is. I spend a lot of time on research, but not so much time in the lab itself. And the way that I've understood that, and I think this is very important for young people as you're thinking about your career progressing, is I used to love being in the lab, and I still do. But what I have found is that if I spend a bit more, less time in the lab and a bit more time thinking about the bigger picture, I enable more research. So in some ways, it's slightly sacrificial. You give up something you really love to do to get more of something you really love to do.
Okay, thank you for that answer. So we have very limited time for questions today, but I'm going to try to get through a couple more at least. I know there are some people in the Zoom session who would like to ask questions. So Paranjape Manu, could you please unmute yourself, turn on your camera, briefly introduce yourself and ask your question? I'm not sure if I'm pronouncing your name correctly. Paranjap?
Yeah. Hi, Manu.
Paranjap Manu?
Yeah.
Mr. Manu, are you there on Zoom?
Okay. I guess he can't unmute himself.
Maybe he can't oh, sorry, this is my fault. This is absolutely my fault. Okay, you should be able to unmute yourself now.
Okay, I'm ready. I can unmute. Hi, Nergis.
How are you?
Thank you very much for the wonderful talk yesterday and today. And I'm just going to ask about this Newtonian noise, which you make great effort to eliminate. And on the other hand, Newtonian noise is gravitational. So why don't you exploit it? Why don't you create Newtonian noise and then use your extremely sensitive detector to compute post-Newtonian parameters or to confirm Einstein gravity, etc.?
I think I haven't thought about that enough to say if you can or can't do that. But I will say that as long as you want a gravitational wave detector, you want to eliminate the Newtonian noise because it's indistinguishable in the detector from your gravitational wave signal. So that's the real rub there. Now, could you co-opt a gravitational wave detector to be a measuring instrument for the Newtonian noise background? Absolutely. If you can see it in the detector, yes. So so that's, I think, the answer is you could, but that's not what they're you would give up on the gravitational wave
to make precision measurements about the gravitational field, right? I mean, Kip Thorne has this paper from 20 years ago about walking and in the presence of the mirror, and you should be how many 10 meters away or something like that. Well, why don't you come up close and jump?
Yeah. So anyway. Actually, I think people will be very interested to know about Kip Thorne's paper. It's a really good one and really fun. So what Kip Thorne looked at was he looked at the question of what is the gravitational effect of objects, people, for example, near the mirrors, and what he found was that when you get to sufficient sensitivity, better than advanced LIGO, you can't really have people or near the mirrors either, because the mirrors will notice. And in fact, it turns out that you would have one of his results was that you should not walk beside a LIGO mirror, but you can go by it on a skateboard and you'd be fine. And that comes from the impulses.
Right, it's the acceleration. Anyway, thank you, and
thanks for the question.
Good work.
Thanks for the response. So here's another one from YouTube. So from YouTube, the question is, why do the graphs have those jumps in the measurements which are not shown in the model?
Yeah, so I think you mean, instead of jumps, you must mean the spikes in the spectrum, the resonances. Yeah, so the model is very simplified. The models only model the fundamental noises, whereas the instrument, of course, has many other things going on. So let me say what some of those are. So if you look at the resonances or the spikes in the spectrum, at lower frequencies, most of them are explained by just electric line noise, so 60 hertz, 120 hertz, 180 hertz. So the power lines. At roughly around 300-ish hertz, there's a whole family of peaks, and those are to do with, I've told you that the mirrors of LIGO hang as pendulums. So they're hanging from fibers, glass fibers that are under a fair amount of tension. And what you're seeing is actually the guitar string modes of, if you twang those fibers on the tension, those are their normal mode resonances. So you might ask, like, why are you twanging your fibers? The answer is, we're not. They're being twanged by the thermally driven fluctuations of the mirror. So you can, those lines are due to the thermal noise driving the resonances of the fibers. And then there's a whole series of lines that are self-inflicted. These are calibration lines that we inject into the instrument to be able to calibrate. Now, they look rather looming in these spectra. It turns out that they are barely a bin wide, and they're very, very easy to remove in the data. And therefore, you don't lose any data in the analysis from removing them. So they look, they loom large in the spectra, but in the data analysis, they're not a big issue.
Okay, thank you. I think we can do one or two more questions. I saw that Professor Nick Cowan had his hand up a moment ago, but maybe he's decided not to ask a question. Nick, if you'd like to unmute and tell us what your question is now, you're free to do so. Or if you prefer not to, I'll go to the YouTube question. Okay, maybe he's preoccupied. So the next YouTube question, which I think is going to be the last, that's all we have time for today, is how difficult is it to keep ELISA's position steady for accurate readings? Will that be one of the greatest challenges? And E is in brackets, so LISA or ELISA.
Yeah, E is in brackets because sometimes there's an E there and sometimes it goes away and then it comes back. So yeah, so that's a good question. So the way that LISA works is a little bit different than the way that LIGO works. In LISA, there's a laser on board each of the 3 spacecraft, and each spacecraft shoots a laser at its neighbor, and the neighbor that receives that laser light compares it to an accurate onboard clock. And so the ranging for LISA is that the LISA distances can drift in and out by large amounts. I actually don't even recall how many, but because the LISA, the way that the measurement is done is they're literally counting fringes. So the actual drifting in and out further apart from each other doesn't make a big difference because you're able to count how that drifting is going.
Okay, thank you very much. I know I said that was the last question, but then I saw there's another one that will take very little time, I think, for you. So the last, very last question comes from YouTube as well. It's, hi, I'm a first-year undergraduate student. I would like to ask, what are some good books and papers that someone could read to gain a firm grasp on the concepts covered in this presentation?
Yeah, so another great question. So look, if you want to know about gravitational waves and how gravitational wave detectors are put together and some of the science, I highly recommend Peter Salson's book. I think it's called Interferometric Gravitational Wave Detectors, or a title like that. The author is Peter Salson. If you want to get a handle on the quantum mechanics, first of all, you'll have to get through to a semester or two of elementary, of introductory quantum mechanics. I actually shouldn't say elementary quantum mechanics because I think nothing about quantum mechanics is elementary. It's the most weird, spooky, crazy stuff. So you just have to wrap your head around it. But once you get through Intro Quantum, a very nice book for quantum optics and thinking about the quantization of light, which is where all these concepts of squeezing and coherent states and so on come from, is a book by Jerry and Knight. I think it's called Introductory Quantum Optics. So those would be my 2 go-tos, and those are essentially the books that I give to new students in my group. I say, this is the starting place for you. So
thank you very much. That's very valuable information. Sometimes people just don't know where to start. So that's really nice of you. So thanks once again. And please, everyone on YouTube, everyone in Zoom, if you haven't already expressed an outpouring of emotion and appreciation for the talks, please keep going. I'm sure Professor Mavalvala will appreciate reading it later. And before we sign off, I just want to remind everyone that we will have another colloquium at the same time on Friday next week. Next week's colloquium is going to be on biophysics, and we're going to have Professor Melika Lakadamyali from the Department of Physiology at the University of Pennsylvania, talking about visualizing the inner life of cells with super resolution microscopy. So please come back for that. Same Zoom link,